Hi, I'm Michael Mayr, a researcher at the Software Competence Center Hagenberg, and I would like to present our paper called Abstracting Process Mining Event Logs from Process State Data to Monitor Control Flow of Industrial Processes. In the following slides, I will specify the problem and provide some essential preliminary information concerning the data our research is based on, the applicabilities of process mining and digital twins in industrial manufacturing, and the problem of using continuous process state data for process mining methodologies that normally only operate on well-defined and discrete event log data. In the next step, I will talk about a term called event abstraction that aims to bridge the gap of continuous process state data and discrete event log data. Furthermore, I will talk about the term event log-aware digital control flow twin, its definition, and the methodology, as well as the possibilities such concept provides. Last but not least, I will showcase some results on synthetically generated data to demonstrate the overall methodology, and at the end I will give a conclusion as well as discuss problems and future steps of this research. In this paper, we present an approach for control flow discovery and monitoring of continuous process data using a novel combination of time series data mining, process mining, and concepts of data-driven digital twins. Our method builds upon an event abstraction using unsupervised cluster analysis, which are performed on process state data in order to provide a statistically supported process monitoring solution for cyclic manufacturing processes. This serves as a basis for the development of data-driven and event log-aware digital control flow twins. And we apply these concepts on continuous sensor measurements that ought to describe recurring manufacturing events. So before going into the details of the proposed concept, I want to give insight into the databases of this research. The data we are using can be described by a concept called the product state-based view, which provides essentially a structure for product and process-related data in a multi-stage production process. So process state data describes the process-related data, for example, temperature measurements for heating or pressure measurements for forging and so on and so forth, whereas product state data describes product-related data, for example, metadata of the produced product, for example, material composition, or also quality control data and so on. So process mining in general operates on well-defined event logs. These event logs capture an operational process in a discrete sense and provide a process-centric view. So event logs are normally composed of an process identifier, activities, as well as start and end timestamps. And on basis of such data, one may answer questions like, what are the highways in the process? Where do machines and machine operators, for example, deviate from the expected or idealized process? Or where are the bottlenecks and what factors influence those bottlenecks? In the role of digital twins is quite broad, but in this context, we define digital twins as a virtual replica of a physical entity that understands its current behavior and can detect deviations on sensor level. Such concepts can be used for answering questions like what is the current behavior of the model system, where do sensor measurements deviate from the expected or idealized measurements, how does the system react to changes, so what if analysis, so what if I change this parameter, how does this system react to this change, or why does the process deviate from the normality and where, so kind of a root cause analysis. In this slide, I want to clarify the problematics of utilizing process mining methodologies based on continuous process state data In the first table, we are seeing a high-level event log describing the manufacturing process and its events in a discrete way. We can see in the first column the case ID, which specifies a specific cycle. Furthermore, we can see discrete events that are performed at certain time steps identified by an event ID, and a collection of such events is seen as an event log and can be utilized by various process mining techniques. In the image to the right of this event log, you can see the corresponding process state data which describe these events at sensor level. So by modeling the event's behavior, we may enhance this event log using statistical descriptions of the underlying sensor values. However, we observe that in high-level event logs, not all events are captured, or the high-level event logs are incomplete. And here comes event abstraction into play. So we do not rely on a given high-level event log, but we rely on continuous process state data, where we aim to extract the information needed for creating such a high-level event log by using statistical descriptions of the observed recurring patterns in the sensor data. The resulted event log can then be in turn interpreted by various state-of-the-art process mining techniques, and by using an event abstraction on continuous sensor measurements, we combine low-level time series mining results with high-level process descriptions. The general goal of event abstraction is to bring fine granular data to a higher level of abstraction, so enabling easier interpretability and a different view on the process. All in all, the research is quite sparsely in the context of mapping continuous data to discrete events, where most research in the past years has been conducted in the context of discrete to discrete mappings. But in this case, in our paper, we focus on the abstraction of discrete events from continuous measurements, where we follow an abstraction methodology proposed by Eck. So to summarize, we introduce a term called data-driven and event log-aware digital control flow twin, which is able to discover and monitor the high-level process on basis of discrete events, as well as low-level process on the basis of sensor data. So we combine the two fields, process mining and digital twins, by mapping reoccurring patterns or reoccurring process states in sensor data to statistically backed activity instances, which is called event abstraction. Furthermore, we utilize the underlying statistics that are calculated during this event abstraction step for monitoring and discovering deviation of normality within similar behaving activity instances using digital twin concepts. The data-driven and event log-aware digital control flow twin consists of the following stages, namely the abstraction of the process states, which is composed of feature selection, segmentation, statistical segment description, and clustering. The creation and the statistical enhancement of event logs, which relies on domain knowledge, and furthermore, the discovering and monitoring of the enhanced event log using process mining and digital twin methodologies. The enhanced event log is used for process discovery to showcase the high lanes, so to say, of successive process states that occur during the manufacturing process. And furthermore, the statistical properties of the clusters that are formed in the event abstraction step are used for deviation detection at sensor level. In this slide, I will go into the details of the event abstraction step and the creation of the corresponding event logs. And you can see in this slide there are two process state features, namely a feature capturing the exhaust flow rate and another feature capturing the heating temperature. We split the features into k-sized segments where statistics like mean, trend, or standard deviation are calculated for each segment. And we cluster similar behaving segments based on those calculated statistics using a simple k-means clustering algorithm and assign labels to those clusters using domain knowledge. This is shown in the bottom left table, and in this example we extracted 4 clusters, each of them representing a specific process state that is occurring periodically throughout the observed sensor measurements. The optimal number of clusters that need to be extracted from the process state data is approximated by maximizing a silhouette score, where an example silhouette plot is shown at the top right corner. On basis of those clusters, we create the corresponding discrete event log describing this cyclic manufacturing process, which then can in turn be interpreted by state-of-the-art process mining methodologies. In this context, we utilize process mining for discovering the highways and visualizing the highways of the process states. Apart from the appliance of the abstracted event log to process mining, we can also utilize the statistical properties of the formed clusters to detect deviation from the learned cluster norm at sensor level. So this is part of the previously mentioned concept of digital twin. This means that we utilize the centroids of the clusters that are formed in the event abstraction step to compare which process states in a cluster deviate from the expected or idealized process state learned from historic data. So the plot to the right shows a visualization of this deviation to the learned normality, where samples in the cluster are normalized univariately. In this slide, we showcase the proposed methodology based on a simple synthetically generated process state example. We generated 100 cycles of an example process that consists of 5 pre-inserted process states. Those process states are generated such that they are distinguishable by differences in mean, trend, and standard deviation, and we added deviations to set process states at 20% of cycles to simulate an anomalous process state. In the graph below, one can see the resulting process map, where each of the nodes observed in this map is composed of a cluster that contains similar behaving process states. Each of the nodes can be described by the calculated cluster centroids. In this example, we clearly see the highway of the process for the generated 100 cycles, and we also observe the synthetically added deviations from a high-level point of view. As part of the summarization of the methodology, I also want to give some insights into the problems we encountered. So the first problem is that we need to specify a higher number of clusters than approximated by the silhouette, as we also want to discover more sparsely occurring process states. And if the number of clusters is too low, we would miss those states. So this leads also to more created clusters, and thus a higher amount of work for labeling and eventually also rejoining falsely labeled or falsely separated clusters. We also see problems with concept drifts. This is due to the fact that we expect to learn the normality of process states in historic data. However, in case the definition of normality for specific process states change over time, we would not be able to capture this drift adequately with the proposed method. Also, we observe in our synthetic example process that interpreting cluster statistics takes time, making a complex real-world process with a high number or potential high number of different process states quite challenging, especially for domain knowledge experts. Using the technique based on constant segmentation may not capture the process state's exact start and end time. However, we think that this approach provides enough approximation to enable interpretation using existing process mining techniques. Furthermore, we may not describe complex process state characteristics adequately in a real-world scenario when using cluster statistics solely. We think that we may overcome the mentioned challenges and limitations by utilizing a structure based on hidden Markov models. The future steps are currently an applicability study in real-world manufacturing systems, and also investigating how can we do this event abstraction using a probabilistic method, for example, like hidden Markov models, or other methods like matrix profiles to generate those events from this continuous process state data. And furthermore, we want to investigate failure pattern and root cause analysis based on this methodology. So, as a conclusion, in this paper, we present an approach for control flow discovery and monitoring of continuous process data using a novel combination of process mining techniques with concepts of data-driven digital twins. Our method builds up on data-driven event abstraction using unsupervised cluster analysis, which are performed on process state and product state data in order to provide a statistically supported process monitoring solution for cyclic manufacturing processes, which serves as a basis for the development of data-driven and event log-aware digital control flow twins. So the methodology proposed by Eck serves as a basis for the research conducted in this paper, and we extend this proposed approach by including time series-based process state and product state data in this event log as additional dimensions. As well as, in addition, we utilized the computed cluster statistics, which were formed in the event abstraction step in the context of data-driven digital twins. And we test our method on synthetically generated cyclic manufacturing data with artificially injected process state deviations and visualized abstracted event log using a process map. We currently see considerable potential in incorporating continuous time series measurements into the context of process mining for the appliance in the industrial manufacturing domain for process discovery, conformance checking, and possibly failure pattern and root cause analysis. In this slide, you're just seeing the references. These are not all of the references which were referenced in the research paper, but all of the references mentioned in this presentation can be found here. Yeah, thank you, and have a nice day.